Hi, everyone. We're wrapping up our Chapter 15 content today, and we're going to make sure today that you have some sense of what the difference is in approaching a problem using confidence interval methodology or approaching a problem using hypothesis testing methodology. So let's talk about the differences first, whether you're using an interval or a test. When you are using a confidence interval, your starting point is the data. The data drive everything that you do with a confidence interval. You don't start with any preconceived notions of what you would expect to see. You just let the data guide you, and you have a formula that you plug data-related values into. And therefore, we think of a confidence interval as a data-centric quantity. Whereas with hypothesis testing, we think of it as a model-centric procedure. And the reason for that is you always have a null hypothesis. And under the null hypothesis, you are specifying what the status quo is, what the preconceived belief is. Specifying that value means you are creating a model for the data. So in contrast to a confidence interval, which makes no such starting assumption, with a hypothesis testing, you're trying to check whether that starting assumption under the null hypothesis fits with the data or not. So you're checking, is this proposed parameter value, the null hypothesis value, is that consistent with the data that you have observed? But even though these two methods have very different starting points, they will most of the time give you consistent interpretation. So I think the biggest difference is just recognizing the way we've discussed confidence intervals and the formulas we have for implementing them is we're always doing a two-sided confidence interval, because we have the formula estimate plus or minus margin of error. We take a step in each direction away from our estimate. That's what we mean by two-sided. So if you are doing a hypothesis test with a two-sided alternative, there is some equivalency there to a confidence interval that is two-sided the way we've done them. And specifically, if you do construct a confidence interval, say you're doing a confidence interval and you specify beforehand you're going to do one with confidence level C%. If the proposed parameter value, the null hypothesis value, if that is inside the confidence interval, then we fail to reject the null hypothesis at the 100 minus C% evidence level. What do I mean by this? Let's say your null hypothesis is that the population mean is equal to 5. Right, this is just an example for illustration. And let's say you construct a 99% confidence interval, and that is the range of values from 4.8 to 6.1. Now, notice that the null hypothesis value is inside the confidence interval. That means we would not reject the null hypothesis here, and our evidence level would be the 100% minus the 99%, so a 1% evidence level that we also call a level of significance, right? So doing a 99% confidence interval is equivalent to doing a two-sided hypothesis test and specifying a 1% level of significance or a 1% evidence level. That's like the equivalent of the burden of proof in a court case, right? That's the specified reasonable doubt level. So let's look at a quick example here. Not going to run through these calculations, but it would be a good idea if you sit down with this for a few minutes. Let's say we're investigating a population of healthy adults from a specific population. Now, most of the time, normal body temperature is considered to be 98.6 degrees. But does that apply to all populations in all places at all times? It may not. So this preconceived or the status quo value could be wrong. If we take our sample, the mean of this specific sample of 52 healthy individuals is 98.285 degrees. So you can see the sample mean is a little bit lower than the status quo. Now, we can then construct a 99% confidence interval. And in this particular example, our confidence interval ranges from right at 98 degrees to just over 98.5 degrees. So the upper end of the confidence interval, it misses the value 98.6 by about half a degree. So at the 99% level of confidence, this sample is not consistent with an average body temperature being 98.6 degrees. Could our confidence interval be missing the true value? Yes, that is certainly possible. But we've set a high bar, right? We know when we're using a 99% level procedure, 99% of the time it will capture the truth. So there's only a 1% chance that this is an instance where it's not capturing the truth. But okay, confidence interval tells us here that the value 98.6 is not consistent with this data. Let's see if a hypothesis test gives us the same result. In this instance, if you go and calculate your test statistic, you would do a t-statistic, would have 51 degrees of freedom, and you would get a p-value of 0.0016 or 0.16%. Now, again, if we're using a 1% level of significance or a 1% evidence level, because our p-value is below the required evidence level, we reject the null hypothesis. So again, the hypothesis testing procedure provides us with strong evidence that the mean in the target population is not 98.6 degrees. So you can see here, there is consistency. The confidence interval and the hypothesis testing procedure reach the same conclusion with regards to this specific example. And it's not a blanket statement that they will always agree, but they will very frequently agree. The one instance where you have to be very careful is if you're working with proportions. Confidence intervals use p hat, the sample proportion, to calculate the standard error for the confidence interval, and that's given by the square root of p hat q hat over n. So it doesn't rely on a preconceived value. On the other hand, if you're doing a hypothesis test, now you're calculating SE0, which is the square root of P0 Q0 over N. So confidence interval and in a hypothesis test are not based on the same estimate of standard error because one of them uses P hat, one of them uses P naught. And if these values, these estimated standard errors, if they are far away from one another, then we create the possibility that the confidence interval and the hypothesis test will not be consistent, in that they may give us differing results. So keep that in mind, but you just, if you're implementing a procedure and you're doing both an interval and a test, a good thing to do is to just do a check. How close are the two standard error values from one another? And in fact, we're going to do an example specifically looking at a proportion and do it using both a hypothesis testing way and doing it a confidence interval way. So the data we're looking at is from baseball, and we want to determine whether the data are consistent with there being a home field advantage for one of the teams. So the home team in this instance won 1,308 of 2,431 games. That means the home team won close to 54% of the games played in the 2013 season. So is there evidence to suggest that the home team wins more than 50% of the games? Well, if we let P denote the proportion of games that a home team wins, then we can set up a hypothesis, right? Our null hypothesis would be that this preconceived belief of 50% chance of is true, like there's no home field advantage. But the alternative says they win more than 50% of the game. So this is a one-sided alternative. So before you jump in and do the test, you want to run through and make sure that your assumptions are met. Independence assumption, that could be a bit questionable in this case. The 10% condition, while the 2013 season definitely represents fewer than 10% of all games played past and future, you also have your success failure condition. Please take a minute and go and review these in the previous lecture. But we're happy enough in this case to say we can reasonably assume the normal model applies, and so we can use a one proportion z-test. So how do we implement that? Well, for a test in this case, we need to know what our sample proportion is. I'm just rounding it to 3 decimals in this case. Our sample proportion is 0.538. Our proportion under the null hypothesis is 0.5. And we also need to calculate the standard error for our z-test. This is the SE naught, square root of P naught Q naught over N. So in this case, 0.5 times 0.5 divided by the 2,431 games. And this gives us a standard error of roughly 1%. So we can calculate our z-test, P hat minus P naught over SE naught. So 0.538 minus 0.5 divided by 0.01. And this gives us a z-score of 3.8. So if you visualize that on a normal curve, centered at 0, 3.8 is here in the upper tail, our p-value is the part of the curve that exceeds 3.8. Now, if you go and look up 3.8 in your normal table, that will tell you how much of the curve is to the left of that value. And that ends up being 0.99993. So the p-value is 1 minus that number, which in this case is 0.00007, or even expressed as a percentage, it's 0.007%. That's very small, right? If we had an evidence level or a level of significance of 5%, then our p-value is less than 5%. If the p-value is small, there's a small chance that the null hypothesis is true, and so we reject the null hypothesis. Here you then, if you reject the null hypothesis, remind yourself what the alternative said. The alternative said when proportion is greater than 50%. So yes, the sample evidence is consistent with a home team advantage. That's what it means when we reject the null hypothesis in this case. So because the p-value is very small, it says in this hypothetical world where the truth is 50%, it would very rarely happen that we get an observed sample proportion as large as 53.8%. And so therefore, there is reasonable evidence that the proportion of home team wins is greater than 50%. Now, we could approach the same problem with a confidence interval approach. We again have to check a success-failure condition, but now you can empirically verify how many successes were there, how many failures were there, not based on some hypothetical number, but based on what you actually observed. You can calculate these as NP hat and NQ hat, but they both have to be at least 10. If that holds, then the sampling distribution is reasonably assumed normal. We again have the assumption of independence, randomly selected values, a little bit non-ideal in this case, but because the success-failure condition is met, we can cautiously go and do a 1 proportion Z interval. So what do the calculations look like in this case? Well, our p hat is still 0.538, but now we need to use the standard error appropriate for the confidence interval, which in this case would be the square root of p hat q hat over n. So the square root of 0.538 times 0.462, same sample size as before. And even though this uses different numbers, what you'll see is when you round the standard error to 2 decimals, you're getting virtually the same standard error. So what that tells you here is the standard error under the 2 approaches is nearly the same. And so you would expect consistency between the 2 approaches. Now, say we're doing a 95% confidence interval. You'll have to go find a Z star value for that. And in this case, that's 1.96. Please go and review that from chapter 13 if you need to. And the confidence interval is then given by p hat plus or minus Z star times the standard error, which in this case means 53.8% plus or minus 1.96 times a 1% standard error, which gives us a confidence interval ranging from 51.84% to 55.76%. So if we were testing a null hypothesis value of p equal to 0.5, it is not inside the confidence interval. So we would again reject the null hypothesis. What's important to remember here is the confidence interval is 2-sided. So the alternative hypothesis here would that be that p is not equal to 0.5. It's different from how we set up the test. The test allowed us to do something directionally because we were hoping to see an increase. The confidence interval here does not allow for that. It is against a 2-sided alternative. But even so, we reach the same conclusion. We find our confidence interval, and in this case, note that the null hypothesis value is not inside the confidence interval, which means we reject our null hypothesis. Meaning, the confidence interval also gives us evidence that there is a home team advantage. Now, practically, how big is this? A standard game is 162 games for a team. Half of those they will play at home. The confidence interval therefore says they can expect somewhere between 1.5 and 4.5 extra wins associated with the 81 games they are playing at home. But of course, each team has the same number of home games. And so to some extent, even if the home team advantage exists, all teams have a turn to have that advantage. So it's not going to be something that manifests as one team having far bigger or far better performance, if that makes sense. I think the important takeaway here is we could do a hypothesis test, we could do a confidence interval, and we reach the same conclusion. Now, we will do a couple more examples in our next live session, looking at both confidence interval and hypothesis testing, and I will see you for that tomorrow.